All right, Algebra 2, Section 5.6 is where we really start to put everything together here that we've been learning so far in this chapter. This is where we really start solving some really complex polynomial equations, combining some of the skills that we've been talking about. Most notably, the factoring that we did earlier in this chapter is really going to be important in this section as well. But also, we're going to get into some of the newer things we've been learning in 5.4 dealing with synthetic division. And you'll see how all of that ties together here pretty soon. But the overall goal is to solve some relatively complex polynomial equations like this one right here, which is the last one we're going to be doing. So let's talk about how we're going to get there. We start off today talking about something that has a really important title if you break it down and think about it, the fundamental theorem of algebra. So theorem is a word you guys learned in geometry last year and probably didn't like very much, but it's a mathematical rule or a law that has been proven. So we know that it's true and we know why it's true as well. And calling it fundamental means it's pretty darn important. So here is the fundamental theorem of algebra. Like a lot of your theorems from geometry, it's written in if-then form. And here's the hypothesis of your theorem right here. If p of x, which is the notation we've been using all chapter to denote a polynomial function, has a degree of n, where n can be any positive whole number in a polynomial. So if your function has a degree of n, then that polynomial function, p of x, has n roots. And remember, guys, when we talked about the word roots back in section 5.2, I want to say, we really talked about how there's some connection there between the words roots and then the word zeros, and then also solutions to an equation right there. So those three things are all connected as well. And also, this is going to become important later on here, x-intercepts when you're looking at a graph. So those four concepts are really more or less the same thing, everybody. Roots, zeros, solutions, and x-intercepts. So this is something I've been trying to get across to you guys so far in this chapter, and I think most of you guys are catching on to it pretty well, that whatever the degree of your polynomial is, that's how many roots or zeros or solutions or x-intercepts you should probably expect. However, there are three little things I want to make sure that everybody knows. Here's the first little bullet point right here. Out of those n roots, they can be either real, and the real ones can be broken down into either rational numbers, like for example x equals 5, or they could be irrational, like x equals the square root of 5. Okay, they can be kind of ugly that way, or they could be imaginary numbers. That could be something like x is equal to 5i. And if you recall, the only way we end up with imaginary numbers, such as a 5i, is if you end up trying to take the square root of a negative number. So there's three different types of roots that can happen, okay? Rationals, irrationals, or imaginaries. All right, so let's keep that in mind. Then the second bullet point I wanted to bring up right here, roots can occur multiple times. And that's when we talked about the concept of multiplicity. So sometimes people feel like the fundamental theorem of algebra is lying to them because this tells us that if we're dealing with a third-degree polynomial, we should have three roots. Now that's true, but sometimes because of multiplicity, it might appear that a third-degree polynomial only has two roots. Well, that's because one of them actually occurs twice. So it's really, let's write this note down right here, that the sum of your multiplicities, that's a hard word to write out, sum of multiplicities has to equal your degree of your polynomial right there. And the third bullet point I wanted to make right here, this is an important one, is that your imaginary roots have to occur in pairs. Now, if you recall, we talked about this just a second ago, the only way to end up with an imaginary root is if you end up, let's say, doing the quadratic formula, and you get x is equal to, let's keep this simple now, the square root of negative 25. Well, that becomes a plus or minus, and then that would be a 5i. But every time you take the square root of a negative, there are two results to that, one positive and one negative. And that's why your imaginary numbers have to occur in pairs or even numbers. So that's a really important thing to keep straight as we're going through this. Your imaginary numbers, you can have two of them, you could have four of them, but you could never have one or three imaginary roots because 1 and 3 are odd numbers. The number of imaginary roots has to be even. So with all that in mind, let's move on to our first example. So let's take a look now. We're going to run through 4 examples now for the rest of this section that use that fundamental theorem, and the directions are going to be the same for all of them. We're going to find all the roots of each polynomial equation. So here's our first example. We're going to start with one that's actually very similar to problems that we did back in earlier in chapter 5. In fact, we may have done this exact same problem right here. Let's talk about it. X cubed minus 3x squared plus x minus 3 is equal to 0. By the way, I should point all this out. All of these polynomials have to be equal to 0 in order for us to be able to solve them. If they're not, like just for example, if this was an 11 over here, the first thing you would need to do is subtract that 11 from both sides and then combine those two terms right there to get it equal to 0. So let's remember that as we're moving forward. Okay, now before we dive into this, there are 3 things that I want you guys to think about in advance. And if I'm not mistaken, I think that the homework you guys are getting on section 5.6, that worksheet, is going to ask you these questions outright on the very first problems on the worksheet. First of all, how many total roots are we expecting here in this polynomial? Well, what we wrote down on the last slide, because of the fundamental theorem of algebra, is whatever the degree of your polynomial is, that's how many roots you should expect. We are dealing here, guys, with a 3rd degree polynomial. That means that we should be expecting a grand total of 3 roots. That's the main takeaway from the fundamental theorem of algebra. However, those 3 roots, we said, can be either real or imaginary, and we need to talk about how many we could expect. So the next question I'm asking you guys, how many of those 3 roots could possibly be imaginary? Well, let's go back to this 3rd bullet point that we wrote right here. Imaginary roots have to occur in pairs. There has to be an even number. So you want to ask yourself, what even numbers here could we come up with that are less than or equal to 3? Okay, we could have 2 imaginary roots. That's an even number, less than or equal to 3. Or, people forget about this one as well, 0 is an even number, you guys. That is also less than or equal to 3. You couldn't have 4 imaginary roots because there's only 3 in total and 4 is too many. And you can't have a negative number of imaginary roots. That wouldn't make any sense either. So we're going to have either 2 or 0 imaginary roots. Now, how many possible real roots? Well, let's remember that out of these 3, every root has to be either imaginary or real. So if we were to have, let's say, 2 imaginary roots, let's think about that. 3 total. If 2 of them were imaginary, that would leave 1 real root. I just did 3 minus 2 and got 1 there. Or let's do the same thing. With 3 total roots, if 0 of them were imaginary, 3 minus 0 would tell me that we could also have 3 real roots right there. Okay, so what I want everybody to notice right here is that the 2 and the 1 go together to add up to 3. So out of the 3, there could be 2 imaginary and 1 real, or these guys go together here as well. Out of the 3 total, we could have 3 real and no imaginary. So those are the only 2 possibilities we could have right here for how many real and or imaginary roots that we have. Okay, let's get into it, guys. We're going to go ahead and try to start solving this polynomial equation right here. And good news for you guys, nothing has changed in terms of where we were earlier in the chapter. The first thing you always want to look for is, can I factor this polynomial equation? That's the fastest and best way to be able to come up with all of your roots. So let's take a look at what we're dealing with right here. We've got 1, 2, 3, 4 terms in our polynomial equation. That already gives me a hint as to where we're going to go with this. First things first, you always want to look for a GCF. We don't have one here. There's nothing that divides out of all 4 of those terms. So then, with an even number of terms, 4 being the most common right there, we want to think about grouping those together. So let me rewrite this polynomial. X cubed minus 3x squared plus x minus 3 is equal to 0. And what we like to do is try to group the first 2 together and then the 3rd and 4th terms together. Now, I warned you guys back when we did this in I think that was 5.3 if I'm not mistaken. If this is a minus sign right here, you've got to change this sign right over here. But that didn't happen in this case. With a plus in the middle, This is what we like. So now let's take a look at each of these two binomials and let's see what we can pull out. From these two terms right here, the GCF we could pull out would be an x squared. And then in a set of parentheses, what's left over? That's going to leave us with an x minus 3 after we pull out the GCF of x squared. Then this plus sign comes straight down. And now, this is kind of a weird one right here. There is no GCF that you can take out from x and then this minus 3 right here. So technically, your GCF right there is a 1. Now, you'll see why I wrote that in just a second. Now, you're not really dividing anything out if your GCF is a 1, so we still end up with an x minus 3 in parentheses there. And the only way that grouping would work is if this binomial here and this binomial right here happen to be the exact same thing. And sure enough, they are now. So we grab those GCFs right there, I should say that GCF, and we pull it out in front. So the x minus 3 gets yanked all the way out in front, and now in parentheses, what's left over? We have an x squared left over from the first term here. And from the second term, after we pull out the x minus 3, we have a plus 1. And that, you guys, is as far as you can factor this particular expression right here. So we talked about doing a better job of reading directions. If the directions just said factor this expression, we'd be done. But our directions here want us to go further. We're supposed to find all the roots of the polynomial. So now that we have factored it fully, we have to invoke something called the zero product property. And if you don't know what the zero product property is, it's not the end of the world. You know it, you just probably don't know it by name. The zero product property says you take each factor, and we came up with 2 right there, and you set each one of them equal to 0 and then solve. So I'm writing each factor again now, setting it equal to 0, and now I go about solving. And this one is super easy. Just add that 3 to the other side, and we're going to get x equals 3 as our first root. Remember, we were expecting 3. We've come up with 1 so far. Now, the second equation is a little bit more complicated because we have an x squared. I'm going to subtract the 1 and bring it to the other side and get x squared is equal to negative 1. And how do we undo a square? With a square root on both sides here. The square root of x squared is x. And here's our old friend showing up again. The square root of negative 1. Guys, that is the very definition of the imaginary number I. So I'm tempted to box that up, except wait a minute. We said way back in the day right here at the beginning of this problem that because this was a cubic polynomial, we were expecting 3 total roots, and I've only come up with 2. Why is that? Because I made the mistake, on purpose, mind you, that a lot of you guys make. I forgot there, on purpose, that every time we take a square root, there's actually 2 answers to that. This needed to be a plus or minus I. So there's one real root right there, x is equal to 3, and then we ended up here with 2 imaginary roots. X is equal to positive I, and x is equal to negative I. So when I go back and look at what we wrote in red up at the top of this, this page right here, we were expecting 3 total roots. Yep, that's what we found. On the second line, we were expecting either 2 or 0 imaginary roots. 2 is what we ended up with right there, and those are the 2 imaginaries. And then going along with that, we ended up with 1 real root, and that was the 3 that we came up with right over there. So this is just kind of a mental checklist you guys should be going through, kind of at the end of a problem here, to make sure that your answer makes some sense. Now, real quick, I did say, let me go back to that first slide right here and talk about what we discussed in this box right over here, that roots and zeros and solutions and x-intercepts are all pretty much the same thing. One little exception that I wanted to point out right here, when we're dealing with a problem like this, we did come up with 3 roots, but this graph is only going to have 1 x-intercept, and that x-intercept would happen right here at 3. Imaginary roots, you guys, do not show up as x-intercepts. So this is a function right here, if we were going to graph it, where I would only expect 1 x-intercept, and that would be at 3. Okay, now that really isn't anything that we hadn't done earlier in the chapter, and if I remember this right, I also think this problem is going to be one that's fairly similar, although maybe just a little bit more complicated than some ones that we did earlier as well. Although, The fact that this is a 5th degree problem might scare you guys a little bit, because I don't know that we did anything like that. So x to the 5th plus 3x cubed minus 4x is equal to 0. Let's make a quick little checklist right here over the side, guys. How many total zeros should we be expecting? Whatever your degree is, that's how many total roots you should be finding. We should have 5 right there, okay? As far as the possible number of imaginary roots, remember, that has to be an even number less than or equal to 5. So that could be 4, or let me just keep going down by 2. Could be 2, or it could be 0. Okay, that's what's going on right there. And then the total possible number of real roots is just this number right here minus these 3 numbers. 5 minus 4 is 1, or 5 minus 2 is 3, or 5 minus 0 is 5. So this is what I'm expecting to find here, guys. Let's keep all that in mind. As I said on the previous example, the first thing you want to do in any problem is try factoring. You'll see on the next example what happens when factoring doesn't work. And the first step to any factoring problem is to pull out a GCF. Well, from these 3 terms, it's not much, but they all have a common factor of x. So I'll bring that out in front, and that'll leave us with x to the 4th plus 3x squared minus 4 is equal to 0. Now remember, just because you've done some factoring doesn't mean you're done factoring. It is entirely possible that what you're left with inside those parentheses could also be factored further. And I think that's the case right here. This is what I kind of referred to as the 4, 2, 0 pattern right here. X to the 4th, x to the 2nd, and then no x's at all. We're dealing with a constant. When that happens, you guys, this is in effect kind of a quadratic trinomial kind of on steroids right here. It usually will factor then, not always, but usually into the product of 2 binomials just using reverse FOIL. So let's think about that. What times what is going to give us x to the 4th? Most likely x squared times another x squared. Let's read the signs. This minus right here tells me that these 2 signs are going to be different. One of them will be plus, and one of them will be minus. And now I'm looking for 2 numbers, constants, that multiply to -4 and are going to add up to a positive 3. I don't think that's too hard to come up with. A positive 4 and a -1 should do what we need. Now you can always check your answer with FOIL here. X squared times x squared is x to the 4th. My outer product is a minus x squared. Let me write that there, minus x squared. My inner product is a plus 4x squared. Those 2 like terms combine into a plus 3x squared. And then my last product is positive 4 times -1. That's a minus 4. And sure enough, that matches that, well, it's a quartic trinomial that I was going for. So now that I've checked it, I have no doubt at all that we factored this one correctly and we're on the right path. Now let me repeat something I said earlier here, guys. Just because you've done some factoring doesn't mean that you're done. There's one more thing we can do right here. This binomial right there, you guys, is one I'm hoping you recognize. That's a difference of squares. Both x squared and 1 are perfect squares. It can be factored further. X squared plus 4, though, that's a sum of squares, and a sum of squares cannot be factored. So we're going to end up with x times x squared plus 4, but now the x squared minus 1, hopefully you remember this, factors into x plus 1 times x minus 1, and all of that is equal to 0. So finally, you guys, we're done with all of the factoring. And now that you're fully factored, now we use the zero product property. We take each factor, we set it equal to 0, and we solve. Well, that one is already solved. X equals 0 is our first root that we were looking for. I'm going to skip this guy for right now, and you'll see why in just a second. Let me move on to the third factor here. And again, I know a lot of you guys are able to just look at this and say mentally, okay, if x plus 1 is equal to 0, then x is just equal to -1. And good for you if you can do that. That's perfectly fine. And we'll do the same thing right here. If x minus 1 were equal to 0, x would equal +1. So look at what we've boxed up here, guys. 1, 2, and 3 roots so far, and those are all real. But now, all right, there's a reason I put this one off a little bit. Let's take a look at the x squared plus 4, and let's set that one equal to 0. First thing we're going to do is subtract the 4 to both sides, or from both sides, and get x squared is equal to, negative 4. And now we'll undo the square with a square root on both sides. The square root of x squared is x, and as soon as we go to take the square root of a negative number, we know that we're looking at imaginary solutions here. So here it is, guys. The square root of 4 would be 2. Therefore, the square root of negative 4 is just going to be 2 with an I after it. And I've learned my lesson from the last problem. Every time we take a square root, whether it's a positive or a negative number with a real or imaginary solution, you've got to put a plus or minus in front of that. So everybody, this is our final answer right here to problem B. We ended up with, let's take a look at our red box up at the top. Did we end up with 5 total zeros? 1, 2, 3, and because of the plus or minus, this is actually 2 here. So yeah, we did end up with 5 total zeros. How many of them were imaginary? We said it should be either 4 or 2 or 0. We ended up with, again, because of the plus or minus, 2 imaginary zeros, and that meant then that we should end up with 3 real zeros, and we did. This one right here, this one right here, this one right here. This graph would cross the x-axis how many times? That would be 3, because 3 is the number of real roots that we came up with. So this graph would have 3 x-intercepts. The other 2 imaginary zeros do not show up as x-intercepts. Okay, so the last 2 examples that we've done here, example A right here, sorry, let me shrink that down a little bit. Example A right there and example B, the one that we just finished, both show you guys how you can solve a polynomial equation and come up with all of your roots here if you were able to factor those 2 expressions. So, as fun as that was, really those 2 examples are stuff that we covered earlier on in the chapter. But now as we move into our 3rd example, things start to get just a little bit more complicated, but I think you guys are going to like the way this is going to work out here this year. So let's take a look at this one. X cubed minus 5x squared plus 5x and a minus 4. Let me make a little line right down there, and then I'm sorry, I'll make that easier to see. There we go. Now, notice the note that I wrote for you right here. Sometimes we need a little help to get started, so we can use our calculator to graph and find our first root. What I really should have said right here, that was probably long enough, factoring is the first thing you want to try. This is one, though, guys, if I'm not mistaken, that does not factor. There is no GCF to pull out, and I see 4 terms. So I would normally try to do factoring by grouping here. So don't write down what I'm about to do here, guys, but I have a GCF right there of x squared. That would leave me with x minus 5, gotcha, plus, there is no GCF to pull out right there. Well, that happened in example A, and I just stuck a 1 there, but that leaves you with 5x minus 4 is equal to 0. And what I said, 10 minutes ago, guys, is that factoring by grouping only works if the 2 binomials you end up with right here happen to be identical to each other. And as you can clearly see, x minus 5 and 5x minus 4 are not the same thing. So factoring by grouping doesn't work in this problem. In fact, none of the factoring methods that we have talked about up until this point are going to work here. So what are we supposed to do? You guys might have noticed that we skipped section 5.5. That actually walked you through something called the rational root theorem, which kind of told you a way that you could come up with a whole bunch of possible numbers and guess. We're going to do something different. It's much easier for you guys, so you're welcome. We're going to go to our graphing calculator, and we're going to graph this thing and hope that it has at least one rational root that we can find here. So, for you guys, you're going to go to your TI-84. Unfortunately, I'm on my iPad. I don't have a TI-84. I have Desmos. So here we go, everybody. And you'll notice up in my upper left-hand corner of my screen, I've already typed this function in for you. Y is equal to x cubed minus 5x squared plus 5x minus 4. And I hit enter, and it graphed, and it looked like this. And it certainly would appear, guys, that this graph crosses the x-axis. one time, it looks like, and it looks like it crosses it at a nice rational spot right there at about x equals 4. So I'm hoping everybody sees that right there. Okay, so x equals 4 looks like a spot here, guys, where this graph crosses the x-axis, and that should mean, let me go back to where we were a while ago, take a look at what we wrote in the box on the left-hand side. An x-intercept should be the same thing as one of your roots here. So from the graph, I believe, I'm not certain, and I'm going to double check this, but I believe that x equals 4 is the first root that we came up with. Now, how are we going to find that out? We're going to kill two birds with one stone right here, guys. We're going to go to synthetic division, which we talked about in section 5.4. And we're going to put this value right here of 4 in the box. What comes after the box? All of the coefficients of the original polynomial. We start with a 1 from the x cubed, a negative 5 from the x squared, a positive 5 from the x term, and then a negative 4 at the end. Skip a line, draw a line, and here we go. Now, we had a hunch that 4 was going to work. If it did, I want you guys to think about this for a second before I say it. What would have to happen at the end of this synthetic division process? Right here, we should end up with a big fat 0 right there. We should end up with no remainder if, in fact, 4 divides evenly into this. So let's try it, guys. Let's bring down our 1. I'm going to switch colors on you right here. We'll go blue on this one. And here we go. Bring down the 1. 4 times 1 is a 4. We write that there. And then we add these two numbers together. Negative 5 plus 4 is negative 1. 4 times negative 1 is negative 4, and we add these two numbers together. 5 plus a negative 4 is positive 1. 4 times 4 is going to give us positive 4 here. Add those two together, and sure enough, we ended up with a 0. Now, that accomplishes two big things for us. Number one, and this is really important too, x equals 4 is, in fact, one of our roots to this polynomial equation right here. We weren't certain about it. We just kind of guessed based on the graph there, guys. But now that we divided it out and we got a remainder of 0, now we know for a fact that 4 works. Okay, now the other thing that it accomplished for us, guys, is that we can now figure out the quotient of taking the original polynomial and then dividing out this 4. So let's take a look at this one right here. As we talked about in 5.4, if you started with a third degree polynomial and then divided out something linear, the degree goes down by 1. So my quotient here, guys, is going to be a 1 x, and the power is 1 less than this, so that's going to be a 1x squared. But of course, I don't really need that 1 right there. What's next? A minus x, and then a plus 1 at the end of all that. And because there's no remainder, that's it. That's our quotient. We're going to set that equal to 0. Now, what we've really accomplished, this part isn't hugely important here, you guys, but we just came up with a way of factoring this polynomial right here. Since 4 was one of our roots, x minus 4 is a linear factor of that polynomial. And what's left then is the polynomial quotient that we came up with right here, x squared minus x plus 1. So we looked at this original polynomial 5 minutes ago and we said, nope, it can't be factored. Actually, what I should have said is, we don't know how to factor it, but it actually can be factored into this mess right over here. I'm not going to take the time to verify it, guys, but if you did the double distributive property, you would end up here right back where we started, which would prove that we factored it correctly. Now let's think about where we are here, and I didn't write something down at the beginning that I probably should have. This problem is a cubic polynomial, which means we should be expecting a grand total of 3 roots. We have found one of them so far. There are 2 more that are still out there waiting to be found, and those 2 roots are going to come from this quadratic equation right here. So we need to keep going, and we need to solve this quadratic and come up with the last 2 roots. So how do we solve a quadratic equation? Well, the first thing we would try to do is factoring, but this one also doesn't factor any further than what it is right now. I knew that, guys, because if it didn't factor at the beginning, I don't think we're going to notice that it factors at the end. even if I did try, I'd probably have an x and an x right here. Signs would be the same and both negative, so minus minus, and I would need two numbers that multiply to 1 and then add up to -1. That doesn't work. There are two numbers. There are no two rational numbers that do that. So, that's a mess. Factoring didn't work. So, what are we going to do instead? Well, this is the important takeaway here, guys, from the second part of these notes right here. No matter how ugly it is, any quadratic equation can be solved. Even if factoring doesn't work, we are going to change instead right here, and we are going to use our old friend here, the quadratic formula, okay, to solve this remaining quadratic equation. So let's get working on that. X is equal to, and here we go, the opposite of b. B in this quadratic right here is -1. The opposite of that would be +1. Plus or minus the square root of, and here we go, b squared. Well, we just said that b was -1. -1 squared is +1. So there's b squared minus 4 times an a value of 1 and a c value of 1 as well, all over 2 times an a value of 1. So what does that do for us, guys? X is equal to 1 plus or minus the square root of, and I've always told you guys that right here, you probably want to go ahead and put all of that into your calculator at once, but this one isn't too hard to do in your head. 4 times 1 times 1 is 4, and 1 minus 4 is going to give you -3 all over 2. And there's actually very little left to be done right here. X is equal to, now we cannot leave the square root of a negative, so we're going to make this 1 plus or minus. And guys, since 3 is such a small prime number, it has no perfect square factors other than 1, all we can do here is pull out the I and then just leave the 3 underneath that. The square root of -3 just becomes I root 3, and a 2 stays on the bottom. The only other thing you might be able to do in some cases would be to divide out any common factor that you found here and here and here, but no, there's no common factor we can divide out from 1 and 1i and 2. So the good news is, everybody, as ugly as it is, we are done right here, and those are your, no, I said those, not that, those are your last two solutions in this equation here. And so, let's put a cap on all this, guys. We were dealing with a cubic polynomial right here. We should have expected a grand total of 3 roots. We found one of them right here, and we found 2 more of them right here, 2 because of the plus or minus. Let's not forget about that. So yeah, we found a grand total of 3 roots to this cubic polynomial. That's what the fundamental theorem of algebra tells us we should be seeing. Furthermore, out of those 3, how many were imaginary? 2 of them. And we said that imaginary numbers have to occur in pairs, even numbers, so that's good. And that meant that we had just one real solution right over here. All this checks out. These are all things that can and in fact should happen as we're going through this. Okay? All right, guys, so that's example C, fun one. And let's take a look now at example D. This is the last problem that we're going to do together, and this one's a doozy here, guys. So let's see what's going on with that. This is a here we go, 1, 2, 3, 4, 5, 6 term quintic polynomial. Whew! This is about as bad as it gets here, everybody. We've never seen one this complex. So let's think real quick. We should end up with a grand total of 5 roots. Why? Because we're dealing with a 5th degree polynomial. Out of those 5, how many could be imaginary? There would have to be an even number less than or equal to 5. So 4 or 2 or 0 of those could be imaginary roots. And then just subtract. 5 minus 4 would give me 1. 5 minus 2 would give me 3. 5 minus 0 would give me 5 real roots. Okay, so I'm looking for a grand total of 5. There could be 4 or 2 or 0 of those 5 could be imaginary. 1 or 3 or 5 of them could be real. Okay, so what do we like to do at the beginning? We like to do some factoring, but I don't think that one's likely to work out real well. Let's take a look at it here, guys. First things, do we see any GCF? No, there's nothing we can pull out from this entire thing right here. And then with an even number of terms, I would think about grouping But what I notice right away, these two terms right here, their coefficients are in a ratio of 1 to 4. That and that's not a 1 to 4 ratio, and neither is 21 to 30. So grouping is not going to get us anywhere here at all. We're going to go ahead and cheat with this problem, guys, just like we did with the last one, and we're going to let our calculator find the first root for us and see where that gets us. So let me go back to Desmos right here. Let me delete most of what I had right here. All right, and let's start typing in this function here, which started off with an x to the 5th and then a minus 4x to the 4th power. Okay, got it. And then let's see. Now we have a minus 10x cubed. Got to make sure you're getting every detail right here, guys, or we're going to have big problems. So a minus 10x cubed, gotcha, plus 22x squared. So 22x squared, moving right along. Plus, we've got a 21x coming next. And finally, a minus 30 at the end of all that. So I'm going to hit enter then. And there it is. So let's take a look at this crazy graph right here. Boy, it's a 5th degree polynomial, so it has a lot going on right there if I were to zoom out on it. But what I'm really interested in here, guys, is where this graph crosses the x-axis. And as I'm looking at it, it would appear, let's count the number of x-intercepts that we have. It looks like we have 1, 2, 3, 4, 5, which is the maximum number we could expect. Now, let's think about that. Since this is a 5th degree polynomial, we should be finding 5 zeros. And if those zeros, or if those roots, happen to be real numbers, they would show up as x-intercepts. Well, I'm looking at this graph just like you guys are. I see 5 x-intercepts. That tells me that I think all 5 of our roots right here are going to be real numbers. What we need to do is find one that looks like a nice clean whole number and run with that. All right, so it looks to me like I've got a nice clean x-intercept at -2. It looks like maybe there's one at +1, and then off to the right, it looks like there's one at 5. Any one of those would be fine to deal with. I'm going to go with the 5, everybody. I'm pretty sure in looking at that it looks like this graph crosses the x-axis when x is equal to 5. But we're going to find out in a minute if I'm right. So let's do some synthetic division, and I'm going to put 5 in the box. And now all of our coefficients come after that. 1, -4, -10, +22, +21, and a -30. And if we were right about the 5, we should end up with 0 for a remainder. Here we go. Let's bring the 1 straight down and go to town. 5 times 1 is 5, added to a -4 is 1. Times 5 is going to give me a 5 here, plus a -10 is -5. That -5 times 5 is a -25, plus the 22 gives us a -3. That times 5 is a -15. 21 minus 15 is going to leave us with a 6 right here. 6 times 5 is 30. And hey, would you look at that? We ended up with 0 for a remainder. So what does that tell me? The first thing I know, guys, is that x equals 5. That was an ugly 5. That x equals a better 5, there you go, is in fact one of our roots that we were looking for right there. I had a hunch from the graph that it worked, but I didn't know for certain until I did synthetic division, and I ended up now with a remainder of 0. So where are we next, guys? Now, I'm going to ask you to do me a favor. Don't write down what I'm about to do. But the quotient we just came up with has a degree 1 less than 5. So this is really 1x to the 4th. Again, I would not write this if I were you guys. Plus a 1x cubed minus a 5x squared minus 3x. And then that would be a plus 6. So this is the new polynomial that we have to work on. And what I would tell you next is take a look at that polynomial and think for a second, does that look like something that we can factor? My answer to that, probably yours too, no. I don't think so. There's no GCF that we can pull out. It's got 5 terms, which means we couldn't do grouping, and that's really the only stuff that I would think of to do with a big polynomial like that. So we're kind of in the same pickle right now that we were back at the beginning of that problem. So I have more good news for you guys. We're now going to use these same numbers right here, and we're going to do synthetic division. You ready for this? A second time starting right there. And what am I going to put in the box? Let's go back to the graph, everybody. Now, we chose 5, but is there another x-intercept that has a nice clean coordinate? It appears anyway that we'd be able to figure out. Well, it kind of looks like x equals 1 is another spot we could try. So let's go for that. I'm now going to put a 1 in the box right here, and I'm hopeful that this one is going to work out as well. Now, by the way, I don't need to worry about the x or anything right here. This one kind of ends right there. Okay. Let's go to it. Let's bring down the 1, and let's hope we end up with a 0 here. 1 times 1 is 1, plus 1 is 2. Times 1 gives me a 2 right here, plus a negative 5 is a negative 3. 1 times negative 3 is negative 3. We'll add those together to get a negative 6 right here. And then that negative 6 times 1 is negative 6, and sure enough, we ended up with a 0 right there. All right, guys, that means that we guessed right the second time, and x equals 1 is our second root that we came up with right there. All right, we've got 2 out of 5 at that point. Now, let's think about that here, guys. We started with x to the 5th, and the first time we did synthetic division, this quotient was now 4th degree. So where are we right now? This one is 3rd degree. And we're getting lower here, guys, to a point where we might actually be able to factor here. So if we take a look at what we're dealing with right here, if this was an x squared and this were an x and then this were just a constant, now I see something that's kind of cool. The ratio of this number to this number is just 1 to 2. The second number is twice as big as the first number. And the same exact thing happens right here, you guys. This number right here, the second number, is twice as big as the first number. That's important, guys. That's significant. I think we're going to be able to factor this polynomial expression. So I probably should have put a plus right there. And here's what I'm going to do now. I'm going to go now and rewrite this. I don't need the 1 there, but just an x cubed and a plus 2x squared and a minus 3x and then a minus 6. All of that is equal to 0. There is no GCF to pull out, although you should think about that. But I'm going to try to group my first 2 terms together and my last 2 terms together. Although, I mentioned this earlier, if you have a minus sign in the middle, which we have right here, you guys, that is when you need to change the sign of that last term right there. You'll see why in a second. Now, what can we pull out? From the first 2 terms, here and here, we can take out an x squared. And that's going to leave us with x plus 2. Gotcha. What comes next then? Minus. And what can you pull out from 3x plus 6? You can take out a 3. And that would leave you with x plus 2. And all of that, not sure why I switched my colors here, is equal to 0. Now, as we've talked about before, guys, factoring by grouping only works when these 2 terms, this one and this one, have the same factor in parentheses, and sure enough, they do. So we're going to pull out the x plus 2 and bring that all the way out in front. And then what's left from the first term after you've pulled out the x plus 2? X squared. And from the second term, we're going to have a minus 3 at the end of all that, and all of which is equal to 0. So, we've done some factoring by grouping there. Can you factor any further? The answer to that is no. That x squared minus 3 is not a difference of squares because 3 is not a perfect square, and x plus 2 you can't do anything with either. So now it's time for the zero product property. We're going to set x plus 2 equal to 0 and solve and get x equals negative 2. And I don't know if anybody noticed this, but if I go back to the graph over here, doesn't it look like this graph crosses the x-axis at negative 2? I think that's actually my very first x-intercept right there. So we could have guessed that one right off the bat, but this kind of verifies that hunch. And now this one over here, a little bit tougher. We'll set the x squared minus 3 equal to 0. We'll add 3 to both sides and get x squared equals 3, and then we'll take the square root of both the left and the right, and we'll end up with x equals, and good news everybody, there's nothing you can do to simplify the square root of 3, but you do need a plus or minus in front of it there, and we end up with x equals plus or minus root 3. Whew! So let's go back and let's kind of cap off everything we did in this problem right here, guys, we were looking for a grand total. If you look in the upper right-hand corner, we were looking for a grand total of 5 roots, and we found 1, 2, 3, and because of the plus or minus, this is actually 2 right there. So yeah, we found all 5. How many of them could have been imaginary? We said 4 or 2 or 0. It turns out none of them were imaginary roots right there, okay? So we ended up then with 0 imaginaries. We did get 5 total roots, gotcha. And 0 imaginaries must mean that we ended up with 5 real, and sure enough, all 5 of the ones that we came up with are real. Now, just to be clear here, guys, this last pair that we came up with is a pair of irrational roots. The square root of 3 exists, but it's a really ugly number. The other 3, though, were rational. All right, everybody, so that is everything that we needed to accomplish here in section 5.6. The key, especially to these last 2 problems right here, is just to keep whittling away here. You can use your calculator to help you lucky guess at the first root right there, but you keep whittling down your polynomial until you get it to something that either can be factored, like we did in this case here. We had to do synthetic division twice, but then we got it down here to a cubic that we were able to factor, or until you get it down to a quadratic, and even if you can't factor it, you can use the quadratic formula in order to solve that. So 5.6 is a tough section. It's going to take you guys some practice to get through it, but I think you're going to do fine with it. So let's dive in, and good luck, everybody.